Hello, how are you doing? This is Mike again, and we're going to go and tackle another Calculus 2 question, volume revolution, discussing volume revolution. And these I find them actually sort of exciting. I like to really dig down in the nitty-gritty and make sure that I'm evaluating everything and I'm not missing any important aspects, because it really is easy to miss things in these questions, but through practice and perseverance you'll be able to definitely start visualizing how to tackle these questions on an easier basis. So the first thing that I like to do with any volumes questions, I like to go ahead and start drawing them out. So notice here we have x plus y is equal to 4. This is a line. X plus y is equal to 4. It's y is equal to negative x and negative x plus 4. Y is equal to negative x plus 4. So this is a linear line, and it looks something like this. I'm going to give myself a little bit more space just to make sure that I can emphasize key points. So here is my x plus y is equal to 4. So I have some very important points here. So I have my y-intercept up here, which is going to be 0, 4. I have my x-intercept here, which is 4, 0. And now I have to see where else this is enclosed, how I create the area. I have to create an area first before I can create a volume. So now I have the line y is equal to 0. So y is equal to 0. I'll do this in green. So this is a horizontal. This is a horizontal line, the x-axis. So this is y is equal to 0. And then I have the line x is equal to 0. I'll do that in blue. X is equal to 0 right here. So now I have created this area right here. So I've created an area right here. So I like just to briefly shade that in just to give myself an idea of what we're looking at. So again, it helps me to get an idea of the type of area. Are we working with a very large area? We're working with a very large area. I'd be expecting to have a very large volume. But we see that if I were to calculate the area of this blue shaded in portion, it's just going to be 1/2 base times height. 1/2 base times height. And the base is 4, the height is 4. So this would just give us a value of 8 something squared, 8 meters squared, 8 inches squared, 8 centimeters squared, 8 decimeters squared. And it could be 8 miles squared too, but I'm thinking about a value of 8. If you get a volume that is 900 million or 825,000 pi, then I'd probably say that's not a good volume for a object that has such a small area. So again, you can just use that you use that as a way to guide and measure your outcome. There's really no checks and balances that maybe you've seen in other past courses like algebra, where you can plug back into the original and see if you satisfy an equation. Here it's just gauging through practice. So now, since I defined the area, I have to see how I'm going to go about rotating this, and we're going to rotate this guy about the x-axis. So I'm going to go ahead and in white, I'm going to indicate by putting my corkscrew right there that I'm rotating this about the x-axis. So this will give me something that looks like this, as such. So notice this three-dimensional figure that I've created. It's I'm going to go ahead and redraw it over here just to make it a little bit easier to see. And now I'm going to have something that looks like this, and this is not a perfect depiction. And then I have something that comes down that looks like this. And if I were to rotate this about the x-axis, I'm going to have something that looks like that. So it just starts looking like a pyramid. That's a horrible pyramid. So there we go. So a little bit more of a pyramid like that. So here, some of these three-dimensional figures take me so long to draw on my tablet, but I do enjoy doing it. So now I think, okay, this is my axis of rotation. My axis of rotation is the x-axis. Next, I like to draw my radius. I want to draw a radius, and this could be a shell method, this could be a washer method, this could be a disk method, but notice this is a solid volume. So I'm leaning to using a disk method because I don't have any holes. This is a solid volume. I'm not going to use washers at this point. I'm not going to use anything but the disk method. I'm just going to start with the disk method and make sure that I can evaluate and first find my radius. Notice I'm going to draw my radius perpendicular to my axis of rotation. So this is my radius, it's perpendicular. So my radius, no matter where or what type of disk I have, is always going to be a value of y. So this is going to be a value of y. So if I were to create another disk here, so this is another disk. If I were to create another disk here, my radius is a value of y, this radius is a value of y, and this little radius is also a value of y. So my radius is equal to y. I like that. I'm rotating about the x-axis, so I am probably going to use a disk method, and I'm going to integrate, since I'm rotating about the x-axis, I'm going to integrate with respect to x. Doesn't mean that I have to use this method. We could have also tried evaluating this using a different method, and some of you cringe when I say the next method, but it's shells, and some of you don't like shells, but I like shells. I'm just going to go ahead and start with disks just to make this easy. And when we integrate this, we are going to use our disk method. So let's go ahead and plan out our integral, and we're going to integrate with respect to x, So next thing I have to do is I have to find my bounds. So if I integrate with respect to x, I'm going to start here at the origin, which is 0, 0. Hopefully we can see that origin. 0, 0, and then I go all the way out to 4, 0. So that's where the line of x plus y equals to 4 will intersect the x-axis. So my integral will be from 0 to 4 of pi times my radius squared. And since my axis of rotation is the x-axis, I'm going to integrate with respect to x. My radius is perpendicular to my axis of rotation, so my radius will have to be defined in terms of x as well. So we're going to go ahead and let y equal to negative x plus 4, y is equal to negative x plus 4, and go ahead and plug in. So we are going to pull out the pi, integrating from 0 to 4 of our radius, which is negative x plus 4 quantity squared dx. The radius is a value of y. Each one of these radii is a value of, is a value of y. So from here to here is a value of y. From here to here is also a value of y. From the base x-axis to the curve is also another value of y. The value of y, the radius, is changing consistently, but it is consistently defined as y. So let's go ahead and expand this out. I'm going to bring this up to the top a little bit so we can see it better. So we're going to expand this out. So we're going to have the pi out in front, 0 to 4. Negative x plus 4 times negative x plus 4. This is going to give us a value of, what is this? This is, we can do u substitution. Yeah, let's do u substitution. So if I let u equal to negative x plus 4, then our du is equal to negative dx. I like this. If x is equal to 4, then I know u is equal to negative, okay, be careful, negative 4 plus 4, and this is giving me a value of 0. And then I'm transforming my boundaries. So then if x is equal to a value of 0, then u is equal to negative 0 plus 4, which is equal to a value of 4. So I'm going to go ahead and transform this here. So my boundary, my top bound, which is 4, is going to transform to a value of 0. My lower bound, which is a value of 0, will transform to a value of 4. And now we will integrate, no longer negative x plus 4 squared, I'm going to integrate u squared du. My du is, and be careful, my du, I need a negative dx, so I have to bring a negative value out to the front. I need a negative 1 here, so I have to multiply by a negative 1 out in front, because my du is equal to negative dx. So now when I integrate this, I will have negative pi out in front, u cubed divided by 3, bound between 4 and 0, bound between 4 and 0. Let's go ahead and pull this down right here. So I'm going to keep my negative pi over 3 out to the front, and I'm going to evaluate my u cubed like this from 4 to 0. So we have negative pi over 3, 0 cubed minus 4 cubed, And this is going to give me a positive 64 over 3 pi. 64 over 3 pi, or 64 pi over 3. So I used a little bit of a different u substitution. If you want to expand this out into x squared minus 8x plus 16, you could have done that as well. I just rather do a simple u substitution, making sure that I transform my boundaries. You must transform your bounds, and then solving simply. So it's just a quick resolution, as a quick formal explanation. What do we do first? We graphed the problem, found the area enclosed, rotated about the x-axis. We then identified that this was a solid volume. My radii, which is perpendicular to the axis of rotation, is defined as y. That indicates to me that this is a very nice problem set up for the disk method of determining the volume of the revolution. The disk method is just going to be pi times the radius squared, integrating with respect to the same axis of rotation. So here our axis of rotation is x. So is the x-axis, so we're going to integrate with respect to x. Be careful, because I know this is the line y equals to 0. So even though we do define the axis of rotation as y equals to 0, the way that I the way that remembers to me, or the way that I remember it, is that if I integrate with respect to the x-axis, I'm rotating about a horizontal line. Disk method, horizontal line, integrate with respect to x-axis. Disk method, vertical line, vertical axis of rotation, integrate with respect to y. It just makes sense to me. And then once I found my bounds, I then performed the integration, solved, and we got 64 pi over 3.